So in this video, we're going to talk about diamond cubic structure, right? So we've been talking about all of these different structures, and if you come to diamond cubic structure, you're going to realize that it's a little bit different from all the structures that you were used to in the way that we're going to explain. So as always, we start with a very complex way of arranging atoms, and we say that, okay, if you look at a specific aspect of this is now too complicated because it's like a diamond, very complicated. But if you just look at very unit cell like structure, you're going to extract something like this. So this is something that we're going to extract for diamond cubic structure. And the diamond cubic structure is basically like FCC, okay? Similar to FCC. So that's a very good start because the unit cell is going to be a rectangle. It's similar to FCC in that we know that FCC is like this, guys. If I'm asking you to draw FCC, you start with your little cube. You draw your corner atoms. You draw your corner atoms. You put atoms at the top, atoms to the side, atoms to the front, atoms to the back, atoms to the right, atoms at the base. So we know that for FCC it's like this, right? But if you take FCC and plug inside 4 atoms, it's strategic positions, right? So if you were to plug in atom there, an atom there, an atom there, at very strategic positions and connect them to other specific atoms, you've just made a diamond structure. So these are what you call the connecting atoms. Like the red parts are what distinguishes diamond cubic from FCC. And these specific little red cubes are inside the structure. So it's a very important starting point to identify that the number of atoms in FCC is basically 4, right? Because we have 1/8 of an atom at every corner, like we talked about. 1/8 of an atom here, right? If you were to take this corner atom and if you were to cut it up, you're going to have basically 8 different pieces going to different cubes, right? And if you were having 1/8 of an atom here, there's going to be one half at the top and 1/2 at the bottom. So you're going to have basically 1 atom at all corners. Okay, if you don't understand this, please go and look at the video that I made for unit cell structure. Start there, it's simpler than starting here, it's a bit more complicated. And then if you look at these atoms, you have half of an atom at the top. So half, that's 1, half, that's 2, half, that's 3. So you have 3 atoms plus 1 atom, so it's 4 in total. And then we're taking FCC and we're plugging inside 4 separate atoms, right? Which are basically these atoms that are going to make this tetrahedral structure. So tetrahedral, because if you connect this atom, you can see that we have 1, 2, 3, 4. That's tetrahedral, right? Where you have something like this. This is what we call, if you've done chemistry, this is what we call a tetrahedral structure. Okay, so the number of atoms then in diamond cubic structure, the number of atoms that we have is basically going to be 4 plus 4, which is going to be 8. So 8 atoms in total. Okay, so that's quite important. And I'm going to give you a little visualization of diamond cubic so that you can see what I'm talking about. Okay, so basically this is what diamond cubic is like. So you can see that we have atoms at the face, so atoms at those faces over here. So you have atoms here at those faces like so, and you have atoms at the corners, which are going to be split 8 ways, and you have atoms inside of this structure connected in a tetrahedral shape. So this atom is connected to like 4 things, and this atom over here is connected to other 4 things. This atom is connected to other 4 things. So this is basically what a diamond cubic structure is. The boring thing about this is that we just know certain things about this. So I'm going to talk about that in a little bit, what we mean by we just know certain things. If you want to find the lattice parameter, so let's talk about this. The lattice parameter is going to be A over here. So it's going to be A, that's the lattice parameter. So it's important for you to find the relationship between A and R. Okay. But we have a problem, right? In diamond cubic, remember we've just shrunk these atoms. But in FCC, these atoms were not touching each other, right? Let's go back a little bit. If you've forgotten, I can refresh your memory. If you look at FCC, these corner atoms were not touching each other. So the distance from this to this was not specifically equal to 2r because there was this little gap in the middle. Okay. And if you look at this, like these atoms are not touching each other. So A was quite difficult to compute. And we ended up using this fact that the cross diagonal is going to be the hypotenuse that we can calculate and stuff like that. So A was a little bit difficult. Now imagine you take this structure and you plug inside 4 other atoms. It's going to make it a little bit more complicated. It's going to be harder for you to see what this structure is going to be about. Luckily for you, you don't need to do a lot of math. Actually, you don't need to do any math to find the relationship between A and R. Because if you were to draw a box like so, if you were to find the cross diagonal, so the cross diagonal is basically this value from one corner in the back to one corner in the front, this cross diagonal like this. So I'm going to call this cross diagonal the hypotenuse. Okay, so to find this cross diagonal, we know that if you go down like this, this is A. Then if you go from this one across the face at the base, this value is going to be, let's say, x. So we know that x is going to be the hypotenuse, the square root of a squared plus a squared. This is a, this is a. So it's going to be root 2a. Okay, so it's going to be root 2a. So you know that the hypotenuse, which is that cross hypotenuse, is going to be the square root of root 2a squared plus a squared, which is root 3a. So the hypotenuse for this diagonal is going to be root 3a. The boring thing is that we as humans observed this structure, and we found out that these atoms that we plug in, they will align directly on the cross diagonal. So these atoms will plug themselves. If you do it like this, they'll stand at the cross diagonal. If you do this and you do that, they'll stand at the cross diagonal. So we just observe this in nature. There's no math that you can do to understand this fact. So if you put an atom which is going to form that tetrahedral circle, those red atoms, they're going to find themselves lying on this cross diagonal over here. And the distance that it's going to have from this corner is going to be 1/4. Right? There's no math, guys. There's no logic to this. We saw it and we observed it. So don't spend, I mean, there's complicated math you can do to figure out why it's 1/4, but I wouldn't bother myself. I'll just take it as it is. So the atom is going to be 1/4 away from this corner atom. So it's going to be 1/4 of this whole diagonal distance over here. And that's just quite important for you to realize. So you can basically go and say, okay, 1/4 of the hypotenuse. So the value of, let's say, y, which is that value. So y is going to be 1/4 of root 3a. So we're done. Root 3 over 4a is basically going to be the specific value that you're going to need. Now, you could ask me, well, what is the distance between adjacent atom centers, which is something that's important that we need to talk about. So the distance between adjacent, I just mean the nearest atom centers. Distance between the nearest atom centers. So you could ask me, what is the distance between the nearest atom centers? Now, if you look at it like this, from this specific perspective, the distance between the nearest atom centers is going to be, so they're going to touch through these atoms. So they're going to touch through these atoms in the cross diagonal. So this atom and this atom are going to be touching, right? Now you might ask me, why is that so? Why is it that this atom, atom number 1, or in this case, this atom, atom number 1 and atom number 2 are the only ones that are touching? It's quite tricky because these two atoms are no longer touching. Like, I can't explain that, right? It's something that we just observed as humans and we just saw that it was happening. So I can't really just explain why that is true. But if you believe me and take my word for it, you can realize that this same distance that we have over here is basically the distance between adjacent atom centers. So 2r, the distance between adjacent atom centers, dc, is just going to be root 3 over 4a. So the distance from one corner, so you can imagine it like this. Okay, so you can picture it like this. This is like one big atom. Like this is one big atom on this corner, and this one, this red blob is one big atom like this, and the distance between their centers, this is R and this is R, so the distance between their centers is going to be 2R. Okay, so that's how you can like picture that. So you can now agree with me that 2R is equal to root 3 over 4A. Okay, so it's going to be easy for you now to find the atomic pecking factor, which is going to be the volume of atoms divided by the volume of the cell, Vc. So the volume of atoms is going to be 8 times 4 over 3 pi r cubed over root, volume of the cell is going to be a cubed over a cubed. So this is 8 times 4 over 3 pi r cubed. And the value of a is 8 over root 3. So I'm doing this, 8 over root 3 r cubed. Okay, you punch that in your calculator, you're going to get 0.34. So for diamond cubic, only 34% is in the cell. And we've observed that atoms actually have this behavior or have this structure. So you can see that we started off with very simple things. As we conclude unit cell structures, you can see that we started off with simple cubic and we built up in complexity. Simple cubic, we got more and more complex. And you can see that, oh, we ended up arriving at an understanding that diamond, cubic, hexagonal are very complex structures that we've just observed in the universe to have a certain pattern. And they're going to have this behavior that we've just modeled and that we've just proved. And that's basically the whole point of this video, to just make you understand all of these different structures that are going to happen.